draw our object on there. So from the side, a sphere looks like a circle. It's going to have some linear velocity v down the incline, and it will have some little radius r, mass little m. Okay. So it rolls without slipping. Neglect frictional losses means energy is conserved. And that's how we're going to solve this problem. There actually must be friction, because if there were no friction, this becomes the sliding block problem. If there were no friction between the sphere or the wheel and the incline, then it just slides down without rotating, and it becomes the old sliding block from chapter 4, where we just let the block go free. Okay, so, and it would have the same answer. It would be, final velocity would be square root of 2 times g times h. Game over. Okay, because no rotation. But we'll solve it the same way anyway. Let's see. Without slipping. Okay. That's the other huge important thing. Without slipping means your linear velocity v must be equal to omega times r, or to rotational. Linear speed must have exactly this relationship to rotational. If it did slip, like that's what's going on when it's too wet outside, or your car goes across some sand, or something's loose, the wheels spin and they have this rotational velocity, but you don't, that doesn't translate to linear velocity. You spin the wheels and you don't go. Okay, for these easy physics problems, and they are pretty easy, once you get the hang of it, we have that condition. Okay, that's an advanced AP problem where you can actually slip and your velocities can be different between spinning and rolling, but this is not the case. So to move forward 1 meter, the outside edge of the sphere must rotate exactly 1 meter and roll without slipping. Okay? Awesome. Well, we're going to solve this with energy. So that means, because energy is conserved, my initial potential energy must be equal to my final kinetic energy. Oh, it seems so simple. Well, that's too simple. Okay, indeed, the potential energy, when the bottom of the sphere is at h, the potential energy is just mgh, like before. Okay, but if I can't move the ball without rotating it, because it's rolling without slipping, I have to have both the linear and the rotational kinetic energy, because I have to roll. Ooh. At first, that looks kind of terrible. I've got v and w in the same equation. Luckily, I know a lot about the object itself that's rotating. Okay, I'm going to scroll down a little bit. Nope, this one. Okay, my favorite thing. Well, w is just v over r, and because I have the same object, the same radius, and it can't roll without slipping, then I can just substitute v over r in for w. I have to be really careful though. My rotational inertia for a sphere is not just mr squared, so it's not as easy as I have a half plus a half mv squared and I just do the whole thing. No, I sphere is 2/5 because calculus. Because if I add up, because of the, you can just think about it, the whole mass of the sphere doesn't have the same lever arm. It's a solid sphere, so some of it has almost zero lever arm. It's right at the center of the sphere. Okay, but some of it has more and more and more, and it's uniformly distributed. So I can't explain why it's 2/5, but I can easily explain why it's less than 1, and even less than a half. Actually, it should make sense. Okay, well then I have to do math. Oh, there's m's everywhere. Let's do one more thing with the m. 1/2 mv squared. That's easy. It's 1/2 times 2/5 times mv v squared. Oh, because if I have w squared times r squared, is that too much substitution too fast? A little bit. Okay, I'll write it out. 2/5 mr squared was the rotational inertia of a sphere. So you plug in rotational inertia. This is I right there. But W is V over R, V squared over R squared. So I cancel my R's. Oh, and there should be plus, not equal. I can't talk and... Right, okay. Well, there we see it. Every term has an M, so it doesn't depend on mass. Don't be mystified if we do an experiment and we're rolling spheres and things of different masses. And they go, oh, why does mass matter? We're proving that it doesn't matter. Okay, the equation says it shouldn't. Okay, let's condense everything. So I have GH, whoa, really big. Can you see that? I have 1/2 plus 1/5, so it should be 10 over 7 V squared. Nope, 7 over 10, sorry. Getting ahead of myself. I had to, because I make a common denominator that's tenths. Alright, GH. Make that small. Shift my thing. Okay. Whoa. Too far. Okay. So when I've spent all my potential energy, when I've sped up the sphere, my V final is just 10 GH over 7, all under the square root. And that's my result for a sphere. We'll come back to this later. What was it for the sliding block? If I just forgot this rotation bit already, that's kind of recovered up by my rotation sign, my recording sign, it would just be 2GH. So notice how this is a fraction, and it's a little bit bigger than 1. And as you get less rotation and less and less and less rotation, you're not going up infinitely fast. You go up to 2. Okay? And that's it. That's the best it can do is not rotate at all and just slide in a straight line. And so the fastest you'll get is square root of 2GH. If every little bit of the mass has to rotate because you have a empty hoop, then you actually get just GH. That's where I would have a half plus a half, because the hoop is mr squared, and it would get just GH. And the disk would be in between, or slower than sphere. But faster than the hoop. We won't work out the fractions really fast. Yeah. Between a hoop and a disk. No, the hole makes all the difference. And the homework asks about one problem that's like an annular ring. That's a hoop that's so thick the thickness actually matters. But no, so if I have a bicycle tire, right? This is why bicycles are done this way. Actually, so the bicycle would have less rotational inertia and could speed up and slow down faster if the mass of the tire was distributed evenly. Like if you had solid tires all the way through. To have the same mass, they'd have to be thinner. But that's actually a big difference, having like a solid disc that's like a plate or something versus having the lightest spokes you can. Like if they could make a bicycle wheel with no spokes and it somehow held its shape, they would do it. Okay, you want all the mass on the outside so that once this gets going, then it's really easy. People can pedal hard for a few seconds and then relax and then pedal gently and the bike keeps itself going because all its inertia is already moving. So it's actually a big difference. We can race them. I have similar massed hoops and discs and you can roll them down an incline and you can see the discs are faster and the hoops are slower. Okay, just when they're just powered by gravity anyway. Okay, so a hoop that has all its mass like a tire right at the edge has much more rotational inertia than you would if you took the same mass and distributed it evenly in a disc. Does that make sense? Maybe, sorta, kinda. I'll see if I can find two that are the same mass. We'll end up doing masses. Good. Any other questions? Okay. Well, if you can crunch your way through rotational kinetic energy, this 1/2 I omega squared. Let me scroll up for a second. If you can fight your way through that, then you actually have enough knowledge to do all the homework. That's all it takes. If you got rotational motion, kinematics, just using the chapter 2 equations, only now they have funny Greek names and they're in radians per second, not meters per second. And you can do this energy, that's all it takes. Okay, so we should just practice up. It's fine if practice takes all week and we test next week. That's kind of what I expect. Okay, well let me know if you need help with homework or if you're stuck on something.